going to continue looking at the chemistry of the carbonyl group. As I said before, I always like to just remind you of the mechanistic stuff that we did time before. And just again to highlight that this isn't too complicated. It's usually very, very similar reaction mechanisms, and they all follow generally the same trend. And what you need to be able to do is work out how to make a nucleophile, how to make something electrophilic, perhaps how to make a leaving group. But the fundamental reaction mechanism is the same for most carbonyl groups. So we either want to have the attack of a charged nucleophile. So our charged nucleophile, usually this is under basic conditions, onto an uncharged carbonyl. So the carbonyl is just a standard carbonyl group. Okay, we haven't had to protonate the oxygen, we haven't done anything. The nucleophile is strong enough to react. We then form this tetrahedral species. So this is the nucleophilic step. And then after that, we will abstract a proton from somewhere, and that will give us our electrophilic step, and we end up with our tetrahedral product. So it's either that, or we take an uncharged nucleophile, using a lone pair of electrons from an uncharged nucleophile, and we'll react it with a carbonyl group that we've activated in some way. So in this case, we have protonated the carbonyl group. So we've done the electrophilic addition first. That's formed this positive charge on the oxygen, which we've seen the resonance structure that tells us that actually the positive charge mainly sits on the carbon, makes the carbon very electron deficient. Then we get the attack of the nucleophile onto that more activated carbonyl. We break the carbon-oxygen double bond. We end up again with a tetrahedral intermediate, and then we deprotonate what was the nucleophile, and we end up with the same product. We've just done it through a different pathway. Okay, so that's the fundamentals of everything. And what we saw last time is that sometimes we have to understand that we might need to protonate the nucleophile, we might need to protonate the leaving group, but the fundamental is the same. The nucleophile attacks the carbonyl carbon, and it's just whether we've activated that carbonyl or not that changes. And so last time we looked at oxygen doing that, so we looked at things like alcohols, and we also spoke about that the sulfur group would do exactly the same reactions as the alcohol. So we didn't go through those, but we know that it would happen. So what we're going to look at today is using a different nucleophile. So we're going to look at using hydrogen as a nucleophile, or the hydride. And then we're going to look at using carbon as a nucleophile. So if you have a source of hydride, so if you can have a source of hydrogen and you can attack a carbonyl with it, what you'll actually do is reduce that carbonyl to an alcohol group. So let's have a look. So what we're saying is, let's just get the pen. So we have our standard carbonyl group. These little wavy lines just means we don't care what's attached to that carbonyl carbon. It could be anything. We're looking at being probably a carbon and a hydrogen at the moment, but we don't have to worry. Whether it's carbon, whether it's hydrogen, it does the same thing at the moment. So they're not bonds, they're just saying, ignore this bit of the molecule, we're focusing just on this carbonyl group. Okay, so we're going to have some kind of H-. We're not going to worry about where that comes from just yet, but if we think of our charged nucleophile as being H-, then we can follow that first reaction scheme I showed you. The idea that a charged nucleophile will attack an uncharged carbonyl. So we can react this charged nucleophile towards the carbonyl carbon. If we form a new bond there, the carbon would have 5 bonds. We need to do something about that, so we're going to break a bond. In this case, we're going to break the carbon-oxygen double bond. Okay, so that's exactly the same as we've been looking at before. What that will give us is O-. Again, just ignore those bits there. So we've added the hydrogen there. And then if we add some water into the mixture, we can protonate okay, and we can get our alcohol group. So that is no different from the mechanism we were looking at before, where we had OH minus before. Now we've got H minus. Okay, we still form this kind of tetrahedral intermediate. Okay, we then use water to protonate that oxygen, and we end up this time, whereas before we had these kind of two alcohol groups, or we had a hemiacetal. Here we've got an alcohol group. Now the only problem is this is a real oversimplification, okay? Because H minus as a species rarely exists on its own. There is possibly one or two examples of reaction mechanisms known where you would get H minus existing as a nucleophile. But it's just showing you that the mechanism is the same. Okay, it's still got this effectively H minus attacking, breaking of the carbon-oxygen double bond, and then finally some way to neutralize that charge at the end, which is protonation. Okay. So sodium hydride, as an example, wouldn't give you H minus. So where we had sodium hydroxide before, gave OH minus, sodium hydride, so NaH, doesn't give you H minus. The way we get H minus is we use what's called a complex metal halide, so something like lithium aluminium hydride. And we've seen things similar to that already, haven't we? We've seen things like the lithium aluminium as the Lewis acid, or we have sodium borohydride. So what I guess I'm trying to say is this is the kind of simplified mechanism. If you can't understand the next slide, as long as you get this, I'll be pleased to see that. What I want to see, though, is you recognise that H minus by itself doesn't exist. So if you're asked this and you just can't remember the bit that's going to come next, you can at least say to me, well, I know that lithium aluminium hydride or sodium borohydride gives us a source of H minus. Okay, and then you can write H minus. Okay, that's what I want you to get. I don't want you to believe that H minus can exist by itself, because then what tends to happen if you believe that is when you start drawing mechanisms, you think, oh, that's fine, I can have this H minus as a leaving group, whereas that will never happen. Okay, H plus, absolutely, but H minus wouldn't happen. Okay, so that's what I want you to take home from this. It's H minus does do this, but H minus doesn't exist. It's there as a function of this complex metal hydride, which we'll see on the next slide. Right. You might have noticed I've picked up a cold over the weekend. It's great, isn't it? It's not full-blown man flu yet, though, so it's okay. If I kind of start collapsing, then it probably is man flu, and if one of you just takes over, that would be great. So, what we're going to do now is show that H minus doesn't exist by itself, but we can generate it using these complex metal halides. So what do I mean by that? What we mean is our friend aluminium again. Okay, can exist with this kind of structure. Again, ignore what those are attached to, okay? That's not me saying there's these funny methyl groups, it's saying ignore what's there. So with the aluminium hydride, what we know is, and we're not going to go into great detail about it because that's a whole nother lecture course on things like transition state metals, and you really don't need to know about that. All you need to know is that the aluminium is a really interesting molecule. It sits in these transition metals, and it can accept and donate electrons more readily than some other things. It's generally to do with the fact that these kind of metals have bigger orbitals. It means that the electrons are more easily available to be nucleophiles, or equally you've got these great big orbitals that can accept another electron without causing too much problem. So what it means is that the bonds in that aluminium hydrogen bond are available to be used for some kind of nucleophilic reaction. Because in this case, the hydrogen is quite far away from the aluminium centre, because aluminium is a much, much bigger atom than, say, a carbon, for example. So what we can say is that this kind of complex metal hydride actually provides us with a source of H minus. And we can say the electrons, there's 2 electrons in this bond here, and both of those can be used as our nucleophile. And that happens really readily, which is why we would consider it to be a kind of charged nucleophile. We don't need to activate our carbonyl group for this to happen. Now, we would need to, if we're going to react the hydrogen, the hydride, then the carbon would have too many bonds, then we break the carbon and oxygen double bond, which will give us our O minus, okay? And we've added this hydrogen here. Sorry, I forgot there's a negative charge there. There's a plus there. Okay, so what we can then say, and this is where it gets a little bit complicated, is you would have this AlH3 left over, and there'll be some lithium plus floating around in solution. And so what actually happens is you form this salt. Okay. So this is just getting a little bit more complex, just to show you this is what would actually happen. Okay. As I said, what I want you to be able to say is if you see these kind of complex metal halides or hydrides, you know that they are sources of H minus, and I'm just showing you why that's the case. So what would happen is you end up here, and instead of just being able to get a proton from some water, you'll see in a minute that for this particular example, we wouldn't have water anywhere near it. Okay. So you can't just protonate that oxygen from water. So what's the next thing it can do? Well, the aluminium, as I've said, is capable of, it's called an amphoteric. It's capable of giving away electrons and taking electrons in. So what happens is you form this bond between the aluminium and the oxygen, and you form this complex. What can then happen is, obviously this aluminium H3 can still do the same thing again. So you could consider that to be AlH2H, with this going off to your carbonyl. Okay, so what could actually happen is that's another source of H. So then if you add another carbonyl to it, you can add, the aluminium can have more than one attached to it. So let me just, so all that's saying is that it's, once you've got one attached, so you've used the lithium aluminium hydride once, the complex that you form here, so this complex can react again. Think of it, like I said, as being, you've got this attacking again, okay? And so you can end up adding a second carbonyl group, basically, to that lithium aluminium hydride salt. So then, of course, you can carry on, you can add another couple, and eventually you end up with you can end up with more of them attached. You can end up with 4 of them there. Okay, so you can add, for every molecule of lithium aluminium hydride you add, it can react with 4 carbonyl groups. So you end up with this complex with 4 things. And then right at the very end, once you've used up all your lithium aluminium hydride doing this, you add water, and at that point what will happen is the water will react with the oxygen here at this point would then be able to pick up a proton from here. This would give you OH minus, which actually would react with the aluminium. But you ultimately, by adding water, you end up with your alcohol. So it is a bit more complicated, but as I've said, what I want from you guys is to recognise it's a source of H-. If you can show me all of this stuff, that would be fantastic. But ultimately, you know, to show me you understand it, showing me that H- comes from lithium aluminium hydride or sodium borohydride is the key thing. Now, as I said, you would, at the very end, you would add the water, and that's because if you take lithium aluminium hydride and you add water to it, what happens is this H- that we've been using for our carbonyl chemistry would also react with the water. So you would find H- would pull a proton from the water, it would pull one of those hydrogens from the water. And of course, if you do that, you produce, well, you'd end up with your AlH3, you'd end up with H2, so hydrogen, and you'd end up with this lithium hydroxide. Now, obviously, if you're producing hydrogen, you have to be very careful because hydrogen likes to explode. So this is why when you're doing anything with lithium aluminium hydride, you wouldn't put water into the system until you had got rid of all of that lithium aluminium hydride. Because by adding the two things together, you create hydrogen, and especially with some of these reactions, you might be heating it a little bit. And so what you end up doing is you end up exploding the lab. The university does not like that whatsoever. Apparently, it's a really bad thing to explode labs and destroy buildings. But that's what can happen with these kind of reactions. Okay? I mean, you'll be pleased to hear that we're going to do a metal hydride reduction during your teaching lab, the next one you do. But of course, we're not going to do it with lithium aluminium hydride because I've just explained to you, if you do it wrong, you could blow up the building. And we really don't want to blow up the chemistry department. Well, no, we don't want to blow up the chemistry department. Okay, so what can we do? Well, we can use slightly different metal hydrides, okay, ones that are slightly less reactive. And so we're going to use one that's called sodium borohydride. So I'm going to talk you through the mechanism of this, which is very similar, okay, but the reason why we're going through this one is when you do this practical if it's next week or the week after, depending on which group you're in, you're going to be using something called sodium cyanoborohydride, which is just a slightly different reaction, slightly different version of sodium borohydride. So you're going to do this reaction in that practical class. So I'm going to show you the mechanism now. Part of the practical class is I want you to do the mechanism then as well, but on the actual example you're doing. Okay, so this is similar mechanism, but the main thing is it's just slightly, it's less reactive. Therefore, it's much safer to use. And the reason is that it doesn't have the same, because it's less reactive, just adding water isn't going to make the H- attack the water. It will work for a carbonyl because the carbonyl is more reactive, okay, but it won't attack the water. So when you do your reaction, you'll see you actually dissolve your sodium cyanoborohydride in a bit of water and a bit of ethanol. So it doesn't have that same explosive result. So what does happen? Well, as I said, it's a very similar mechanism. So if we draw our carbonyl, okay, okay, so sodium borohydride looks like this, which you can see is very similar to that lithium aluminium hydride. If we think about that was AlH3. Yeah, and you can see those things are very, very similar to one another. So it does a similar thing. The electrons in this bond here can be used to attack our carbonyl, and it attacks as if it's a charged nucleophile. Again, that's really key. It means we've not had to activate our carbonyl. But of course, we're going to have too many bonds for that carbon, so we break the carbon-oxygen double bond. So we end up with our O-, and we've added our hydrogen. And again, the same thing happens here. The BH3 that's left, we can just form a complex with that. Okay, so we can form that complex And then again, that can be if you add in another carbonyl, you can add that to it again. Until you end up with 4 of them. And then finally, with a bit of water, you end up cleaving that off and you end up with your alcohol. Okay, so that reaction mechanism is exactly the same as the one we did on the previous page, except we've got this sodium borohydride, which is less reactive and doesn't have the same problems associated with adding water to the system. Because it's less reactive, you can add the water to it. Again, we could go into the details about why that is, but we don't need to worry about that for now. That's, if you're doing a chemistry degree, absolutely, but doing a pharmacy degree, what you need to understand is that this is just a less reactive one, therefore safer to use. And as I said, I can't stress this enough. The most important thing is that you can do the H- attacking, okay? But recognize that that H- does not exist on its own in solution. It's only